Okay, so now let's get back to sort of the proper material of the course. That what we did last time on numerical integration is sort of a digression. It's basically if you want to understand how a computer or how a calculator calculates an integral. That's what the last section was about. But sort of a digression. This section is called improper integrals. Okay. So let's think about what kind of functions you've been integrating so far, right? What have you been integrating? Have you been integrating functions that look like this? Like sort of a lot of discontinuities? No, right? Our functions have basically been continuous functions. So we've been integrating functions that are one, continuous, and two, they've been on bounded intervals, right? Our function's domain with domain some finite interval AB. Okay, and that's the only thing. That's basically the only kinds of functions we've been dealing with. Okay. Okay, so functions that are continuous and on some bounded domain. And remember we had this thing called the extreme value theorem. That said that if you have a continuous function on a domain like this, then something happens. What happens? Then you can say something about the function. What can you say about the function? Jake?
It obtains maximum value, maybe a minimum value.
That's right. So f continuous on a closed and bounded interval, then f attains a max and also attains a min. Okay, so that is, if you have some continuous function on AB, well, there's going to be some maximum value, there's going to be some minimum value, and the function's going to hit those values. Okay, so in particular, notice that f is a bounded function. Right? F is a bounded function. It doesn't go off to infinity. Right? You can't have, if you're continuous on a closed and bounded interval, then you cannot head off towards infinity. Right? Name a function that heads off towards infinity. Can you give me an example of a function that heads off towards infinity? Say x plus 1. Okay, so f of x equals x plus 1. That'll go off to infinity, right? As long as we're talking about on, say, 0 infinity, right? On 0 infinity, this guy will go off to infinity, right? You see that it's continuous, but not on a closed and bounded set, and so it heads off towards infinity, right? Or if you look at a function like f of x equals 1 over x on 0, 1, that also goes off to infinity, right? But you see that neither of these guys is continuous on a closed and bounded set, right? Neither of these guys is continuous on a closed and bounded interval. Okay, right? The only way we could have this sort of thing is if our function is not on a closed and bounded interval, or it's discontinuous. Okay. Anyway, so just to say that the integrals we've been dealing with have been of functions that are continuous on bounded sets, right? And the functions are bounded themselves. Okay, so right, they're continuous, they're on some bounded domain, and the values of the function are bounded. So it's some very simple kinds of functions. Okay, so these are called these we're going to call proper integrals. These are the proper integrals, and today we're going to sort of leave the world of proper integrals. Okay. So integrals can be improper in two ways. Either the function is unbounded, or the interval is unbounded, or both. Sorry, my shoelace is coming down. Okay, so example, if we look at we can look at Ian's example, f of x equals x plus 1, or let's just say f of x equals x on 1 infinity. Or actually, sorry, let me say something like, well, it's okay. It'll work. Yeah, that's fine. Well, let's do this. Say 1 over x. F of x equals 1 over x on 1 infinity. Okay, so this function is bounded, right? The function doesn't go off in value. The function doesn't go off towards infinity, but the domain is infinite, right? So unbounded domain, right? Or the example that we had before, f of x equals 1 over x on, say, 0, 1, right? 0, 1. The domain is bounded, right? The domain is bounded, but the function is unbounded, right? Everybody understanding this? Right. So these are things that we haven't tried to integrate before, right? We haven't tried to integrate these things before, and so that's what we're going to do today. Okay. And the way we're going to do it is sort of the obvious calculus way. So the big idea of calculus is to take things that you know and then combine them with the limit. Okay, right? So, you know, when you talked about, you know, you had something, you knew how to take the slope. You know, back when you were talking about the derivative, you knew how to take the slope of a line between 2 points, right? But you weren't able to take the slope of a line with only 1 point, right? How do you get the slope of the tangent line, right? And so the calculus idea is, well, take your simple idea of taking the slope between 2 points, and then take the limit as the second point tends towards the first, right? The idea of the integral, remember, is you don't know how to get the area under a curve, but you do know how to take the area of a rectangle, right? You do know how to take the area of a rectangle. So take that idea and then, you know, take that idea and then take the limit of it, right? And you get the you get the definite integral. Right? So calculus, there's basically only one idea in calculus, which is take your prior knowledge and combine it with the notion of limit. Okay. Right? That the unknown can be studied as the limit of the simple known. Okay. So we'll extend our understanding of the integral by using the limit. Right? The notion of limit. Okay. So, for example, if we're looking at the integral from 1 to infinity of 1 over x dx, if we're looking at the integral 1 over x dx from from x equals 1 to infinity, somebody says, what's the area under the function 1 over x? Right? You say, well, I don't know how to take that integral, right? But I do know how to take the integral of that function from 1 to b, right? From a to b. I know how to take that integral. So what I'm going to look at is I'm going to say, let's call this thing the limit of the integral from 1 to b of 1 over x as b goes to infinity. Right? That's kind of an obvious thing to do. Right? We don't know, we can't take the integral from 1 to infinity, but we know how to take it from 1 to b, and then let b tend towards infinity. Okay? So take 1 minute and see what happens. Okay, turn to somebody nearby and say what you got. Okay, so what happens? What's the integral from 1 to b of 1 over x? ln x, right? ln x between 1 and b as b goes to infinity, right? So you get the limit as b goes to infinity of the natural log of b minus the natural log of 1, which is 0, right? So you get the limit as b goes to infinity of the natural log. Well, that's infinity, right? That's infinity, right? So the area under this, right, as we look at the area as b goes to infinity, the area under that increases beyond any number that you can choose, right? No matter what number you choose, it's going to get bigger than that number. Okay, right? Everybody okay? Okay. Let's do the other one. 1 over x on 0, 1. Right? So you've got this guy, right? How are we going to define the integral? How are we going to define the integral? How are we going to define it? Right? Take 10 seconds and write down something. turn to somebody nearby and tell them what you wrote down. What do you get? The limit as x approaches 1? The limit of, what should I write over here? A? 1. The limit of the integral from a to 1 as a goes to 0 from the right-hand side. Right? So here's 0, here's 1, right? We want to take the integral from a to 1, right? We don't know how to take the integral from 0 to 1, but we take it from a to 1, right? And we let a tend to 0 from the right-hand side. Okay. Okay. So you do the same thing. You get the limit as a goes to 0 from the top of the natural log of x between 1 and a, right? So you get, as a goes to 0 from the top, natural log of 1 minus natural log of a as a goes to 0, right? Of course, natural log of 1 is 0. So you get the limit of the negative natural log of a as a tends to 0. What is that? As a goes to 0 from the top, what happens to natural log? Becomes, what does a natural log look like? Right. Natural log looks like this. Go to negative infinity, right? And so we get positive infinity again. Okay, so the area, so this area and this area both go to infinity. Okay. Okay. Right. If somebody asks you to integrate, this thing from 0 to infinity, the way you usually do it is you break it up into two parts. You say break it up into, say, 0, 1, and do that guy, and then from 1 infinity, and do that guy separately, right? And if, in this case, both of them turn out to be infinite, and so, you know, we get infinity. Okay. So I should say that whenever you get infinity, we say that the integral is divergent. It's a divergent integral, right? Because it doesn't converge to any limit, right? The limit turns out to be infinite, not some finite number. Okay. So this one also turned out to be this integral is also divergent. Okay, any questions so far? Any questions so far? Yes, Ayende.
Can you spell like the right hand thing again?
Going to 0 from the right-hand side?
Yeah.
So, right, because we want our a to go to 0, right? We want the integral from 0 to 1, right? So we take the integral from a to 1 as a approaches 0 from the right-hand side. Okay, not from, if I wrote like this, then that would mean that a is approaching 0 from either side. Okay, but I don't want that. I want a approaching 0 from the right-hand side. Okay. It would be trouble. It would be trouble if I tried to think about this a from the left-hand side also, because then we'd be talking about the natural log of a where a is negative, right? But the natural log of a isn't defined when a is negative. There is no natural log of negative numbers. So. Yes, Anna.
I don't get how the y equals ln x graph shows positive infinity.
Negative infinity. So natural log of a becomes negative infinity. As a tends to 0, the natural log goes to negative infinity. But we've got negative, right? We've got negative the natural log of a, so we've got a positive infinity. Yes?
Would it be the same as having the natural log of 1 over a?
Sure, sure. We could rewrite this, right?
Okay.
Negative natural log of a, same thing as natural log of a to the negative 1, right? So as a goes to 0, right, from the right-hand side, 1 over a goes to infinity. So we get the natural log of infinity. That's, I mean, natural log of a is, natural log of 1 over a is a goes to 0, which will be infinity. Yeah. That's fine. Okay. Okay. Let me have you do a couple more. Okay. The integral of so this one 1 over x to the p dx. Okay. So p is some positive number. P is some positive number. It'll turn out that this will work. So figure out for what range of p this integral converges. So for certain p, it'll work, and for other p, it's not going to work. We already know if p is 1, this is a divergent integral. Okay. Okay. See what try to do this and see what happens. You'll see that for a certain range of p, it'll work, and for a certain range of p, it will fail. Okay. So take 2 minutes to think about this. Okay, talk with somebody nearby, please. And talk with Mr. Al.
Yeah. It'd be harder. I don't even
Okay, first off, let me ask, why did I say p greater than 0? What if p is equal to 0? Then what will we be doing? It would just be the number 1, right? We'd be integrating the number 1 from 1 to infinity. That's clearly going to be infinite, right? If p were less than 0, what would we be doing? What would we have? We'd be integrating x to some power. We'd be integrating x to some positive power, right? And so that's also, that's even worse, right? That'll be, we'll definitely get infinity if we do that. Okay, right? Because if p is some negative power, we've got x, this is the same thing as x to the negative p, right? 1 over x to the p, same as x to the negative p. If p is negative, we're integrating x to some positive power, right? Like the square root of x or x cubed or something like that. Any of those things is gonna diverge. Okay, so those are sort of the easy ones. We don't have to worry about this. Okay. Did anyone get a range of where p will work? P will result in convergence? Anybody? P greater than 1. P greater than 1. Okay, great. So how do you get it? Let's write this out. The integral from 1 to b of x to the negative p dx, right? And then what happens, right?
X minus p plus 1
Over the same thing, right? As we go from b to 1, right? And so we get the limit of b to the negative p plus 1 minus 1 to the negative p plus 1, everything over negative p plus 1, right? As b goes to infinity. Right? Okay, as b goes to infinity, right? And you see what happens if p is bigger than 1, then this is a negative power, right? If p is bigger than 1, so if p is bigger than 1, then negative p plus 1 is smaller than 0. Right? And if p is less than 1, then negative p plus 1 is greater than 0. Right? We already saw that if p equals 1, we have divergence. Right? If p equals 1, then we have divergence. Okay. Okay. Well, if p is bigger, if the power is less than 0, as b goes to infinity, this thing vanishes, right? If you've got b to a negative power, as b becomes huge, then this thing is going to vanish, right? So you get divergence. You get convergence. Convergence, right? If you get b to a positive power, as b goes to infinity, we get infinity, right? So we get divergence. Okay, so putting it all together, we see that we see that this thing converges for p bigger than 1 and diverges for p smaller than or equal to 1. Julia. Question?
Can you explain again
Yes.
how it converges?
Yeah. Okay. So we've got this thing here. Right? We've got the limit of b to the negative p plus 1 minus 1 over negative p plus 1 as b goes to infinity, right? This is where we are, right? Okay, so if p is bigger than 1, suppose p is bigger than 1, say p is 2, okay? Then we're going to get b to the negative 2 plus 1. Well, that's b to the negative 1, right? If p is bigger than 1, then, right, this is 1 minus p, right? Negative p plus 1. So if p is bigger than 1, then the exponent, negative p plus 1, is negative. Right? So you get b to some negative exponent. For example, b to the negative 1. Right? So example, if p is 2, we get b to the negative 1. Right? Well, as b goes to infinity, you've got b to a negative power, right? You've got b to a negative power, and as b goes to infinity, well, that's just going to vanish, right? That will become 0, right? That becomes 0 as b goes up to infinity. Okay. So whenever this p is big, then this term is going to vanish, and so we'll just end up with negative 1 over p minus 1, right? So this will be negative 1 over negative p plus 1, right? As long as p is bigger than 1. Okay. But if p is if p is smaller than 1, right? If p is smaller than 1, then we get b to some tiny power, like b to the square. Say if p is a half, say, we get b to the 1/2 power, right? Well, as b goes to infinity, that square root of b is going to become huge, right? So you get infinity as b goes to infinity. Okay, so if p is bigger than 1, we get convergence. If p is smaller than 1, we get divergence. Okay, you can sort of see that graphically. Not exactly, but you can. It's maybe believable, right? If you think about 1 over x, you think about 1 over x squared. Well, what does 1 over x squared look like? It'll shrink faster, right? It'll shrink faster because you're dividing by x squared. You're not dividing by x, you're dividing by something bigger, right? X cubed, it's going to shrink faster. X to the 4th, even faster, right? Okay, so you sort of imagine that the higher powers are better. Higher powers are more likely to guarantee us convergence, and what we see is that that's what happens. As long as we have 1 over x, if we have 1 over x to the 1.01, that will converge. Right? What we've just seen is that as long as this power is bigger than 1, we're good. Okay, and that's sort of what you might expect will happen. You know, the higher powers will work, and then the lower powers will fail. Okay. Okay. Let's go on to the last. This sort of leads us up to the last idea in this section, which is something called the comparison test. Okay. So this says that if you have two functions, let f and g be continuous functions with f bigger than g bigger than 0. Okay. So the picture is that you've got one function, you've got another function, and they're both positive, but one guy is bigger than the other guy. Okay? Then, if the integral from 1 to infinity of f What do you think I'm going to say? Hunter?
The integral of 1 to infinity of g of x converges as well.
Exactly, right? If the bigger guy converges, well, certainly the smaller guy is going to converge, right? Then the smaller guy, the integral of the smaller one also converges. Right? And, logically, that also gives you the converse, I'm sorry, the contrapositive, that if the integral of the smaller guy diverges, well, then the integral of the bigger guy must also diverge, right? Because if the integral of the bigger guy converged, then the smaller guy should converge also, right? So we also get the so-called contrapositive, that if the integral of the smaller guy diverges, then of course the integral of the bigger guy must diverge also. Okay, makes sense? That's at least believable? Okay, we haven't really proven this, but we're just going to take it as a fact for now. Okay, we'll prove it later, actually. But I hope that's sort of believable to you, right? You've got two functions, they're both positive. If the smaller guy diverges, then if the area under here is infinite, well, the area under the larger guy is certainly going to be infinite also. Right? If the area under the larger guy is finite, well, then the area under the smaller guy will be finite also, right? Okay. So, for example, just now we were looking at the integral from. We saw that this thing diverges. We saw that this thing diverges. Right? So immediately, since, for example, if I look at 1 over x to the half, well, that's bigger than 1 over x. We know that the integral from 1 to infinity of 1 over x to the 1/2 diverges. Right? Because this thing is bigger than that thing. So its integral, the smaller guy diverged, so the bigger guy is going to also diverge. Right? Is that okay? Right? So, right? Okay, so we sort of got part of the range already. Okay. Let me give you another example. Okay. The integral from, let's say, 1 to infinity of sine of 2x over x squared dx. Okay, actually, let me make this like this. Yeah, I'm going to put absolute values on it to make it positive. Okay. So, does anybody have a feeling about this one? Anybody have a feeling about this? Is it going to converge? Is it going to diverge? Can you compare it against something that, is it bigger than something that diverges or smaller than something that converges? What do you know about the integral of 1 over x squared from 1 to infinity? No, we just worked it out. Remember, if p is bigger than 1, then we get convergence. Right? So this one we actually know converges. Okay. So, can anyone see where we're headed? What do we know about this thing compared to this thing? What do we know about the integrands? Well, this integrand is, if I look at the absolute value of sine of x, the absolute value of the sine, well, that's going to be smaller than or equal to 1, right? So if I look at this, if I divide them both by x squared, well, this is smaller than, this over x squared is smaller than 1 over x squared. Right? Okay. So the integrand of this one is smaller than the integrand of this one, and this integral converges, so that tells me that this integral converges. Right? So since this and the integrand of this one is smaller than the integrand of the other, we see by the comparison test that this converges. Okay, right. We have this integral, and you say, oh look, I can find something bigger whose integral converges. Right, so that tells me that this thing converges. Okay. Is this making sense? I'm not sure. Making sense? Let me, in the last minute, let me do one more example for you. The integral from 1 to infinity of x plus 1 over the square root of x to the 4th minus x. Okay. Does anyone have a feel for this one? What do you think is going to happen? Converge or diverge? X plus 1 over the square root of x to the 4th minus x. Fuzzy?
I think it'll be convergent.
You think it'll converge? Okay. Fuzzy votes converge. Anybody else? Hunter?
I think it'll be convergent.
Okay. Anybody else? The answer is, it's going to diverge. Okay, and you can, so later when you get more comfortable, you'll say, oh look, this 1 isn't going to make much difference, this x isn't going to make much difference. I've got basically x over the square root of x to the 4th, this x over x squared, that's 1 over x. So this is basically like integrating 1 over x. Okay, so your intuition would be, this is going to diverge. Okay, so secretly you think diverges. Okay, and then the way you would, so you have this guess in your mind, and you think, okay, I want to find something smaller than this that diverges, right? So let's find a smaller integrand whose integral diverges. Okay. And because we're out of time, let me just do it for you. Okay, so I'd say, well, look, here is my function. Here's my function. Okay, I'm going to find something smaller in kind of a crude way. I'm just going to throw out that 1 on the top. Okay, that'll make it smaller, right? I'll throw out the 1 on the top. that definitely makes it smaller, right? And then I'm gonna make the divisor bigger by getting rid of this negative x. Okay, I'm gonna make the divisor bigger, right? By adding a plus x to it, right? That makes this thing under here bigger, and so we end up with x over x squared. In other words, 1 over x. Okay, so we found something that's smaller than the guy, and its integral diverges, and so that tells me that the integral diverges. Okay. Okay. So you play some sort of game to try to find something smaller whose integral diverges. Okay, that's it for today. Sorry to keep you over.